Pluto and Neptune. Could a cosmic collision happen? Pluto is a faraway, elusive, and conspicuous planet that was once considered to belong to our solar system. Despite recent groundbreaking assertions from well-known physicists like Neil deGrasse Tyson and Michio Kaku, Pluto has returned to public discussion. They have suggested that this planet could be moving in the direction of a possible collision, with Neptune, of course. But how could such a scenario occur, and what would it entail? Are we witnessing something unusual, an unpredictable phenomenon? Or is there more to this approaching cosmic event? Join us as we explore the possible outcomes of Neptune's collision with Pluto. Pluto, once formerly a planet but later reclassified as a dwarf planet, continues to be a subject of interest and investigation within the vast universe. Recent leading expert predictions have suggested that the orbit of Pluto is alarmingly close to Neptune's. This has prompted astrophysicists Neil deGrasse Tyson and Michio Kaku to alert the public to the possibility of a disastrous meeting between these two celestial bodies, an event which could pose a significant danger to Earth. But how could such a collision even occur? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete one full orbit. Since its discovery in 1930, Pluto hasn't even completed a single full revolution. However, the intrigue doesn't end there. Pluto's orbit is characterized by its distinctly elliptical shape, straying far from the major planet's nearly circular orbits. What makes Pluto's orbit even more unusual is its tilt, inclined at an angle of 17 degrees to the plane shared by the solar system's planets. Pluto's path follows a far more erratic trajectory compared to the more orderly orbits of the others, adding complexity to its orbital dynamics. Perhaps one of the most fascinating aspects of Pluto's orbit is the way it intersects with Neptune's. For roughly 20 years during each orbit, Pluto actually travels closer to the Sun than Neptune does, defying the normative expectations of their relative positions within the solar system. This raises the obvious question: why have Pluto and Neptune not collided? Gravitational forces are the answer. After Pluto's discovery, astronomers quickly set out to understand its strange orbital behavior. Unlike the other planets whose orbits lie close to the solar plane, Pluto's steep inclination and highly irregular shape made it a puzzle. The mystery deepened when it became evident that Pluto's orbit crosses Neptune's. Despite this, Pluto's orbit maintains stability, demonstrating the intricate celestial dynamics of the so-called three-body problem in space. Understanding how three objects like Pluto, Neptune, and the Sun interact gravitationally is essential. It's like trying to predict how their gravitational pull influences one another and ensures the stability of all their orbits. One concept central to this is non-concurrent libration. In Pluto and Neptune's case, whenever Pluto crosses Neptune's orbit, the two bodies are always positioned at least 90 degrees apart. This spatial separation prevents a collision between them. Another contributing factor is orbital precession, which refers to the gradual upward movement of a planet's orbit. Pluto's orbit indicates that when it comes closest to Neptune, or any giant planet, it is significantly elevated above their orbital plane. This provides another layer of defense against potential collisions. An additional factor at play is the VSK wobbling effect, a concept named after researchers who studied how celestial bodies interact gravitationally. This wobbling explains why Pluto's orbit, though seemingly chaotic, remains stable over long periods. The gravitational pull between Pluto, Neptune, and the Sun maintains a relatively smooth trajectory despite Pluto's irregular shape. The VSK wobbling shows that even in the most unpredictable environments, patterns and forces lie beneath the surface to maintain equilibrium. Solving this three-body problem is crucial to understanding the nature of Pluto's orbit, its relationship with Neptune, and the behavior of distant objects in our solar system. Numerical experiments carried out in the late 1980s revealed that Pluto's orbit, despite the presence of stabilizing forces, is actually quite erratic. Small deviations in its initial conditions could result in significant variations in its path over centuries. Nevertheless, these simulations also demonstrated that over incredibly long timescales, millions or even billions of years, Pluto's orbit remains stable. To fully grasp the dynamics between Pluto and Neptune, it's important to consider the gravitational influence of the outer planets like Neptune, Jupiter, and Saturn. In fact, Neptune's resonance with Pluto is unique. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This gravitational resonance helps keep them apart. But Neptune isn't the only player in this equation. Jupiter's massive gravity plays a key role in stabilizing Pluto's path, and Saturn contributes further to this dynamic. These forces working together ensure that Pluto remains on a steady course for potentially millions of years, keeping it out of harm's way. Without these stabilizing forces, the solar system would be far more chaotic, with planets potentially colliding or being ejected from their orbits, causing catastrophic consequences across the solar system. The possibility of Pluto colliding with Neptune in the future emphasizes the depth of celestial mechanics and the importance of studying orbital stability. Through understanding these intricate dynamics, we gain a better understanding of how the solar system works, how gravitational forces shape everything, even for distant objects like Pluto. Even though Pluto's orbit may appear chaotic at first glance, it is a testament to the delicate balance of forces that keep it in place. Exploring space frequently leads to unexpected discoveries, and the erratic orbit of Pluto is an excellent example of the universe's mysteries. The idea of orbital chaos illustrates how a celestial body's orbit can be highly sensitive to its initial conditions. In Pluto's case, even minor modifications to its position or speed could drastically alter its long-term path. Automated simulations have proven invaluable in helping scientists study these behaviors. By modeling how Pluto and objects like Neptune influence each other gravitationally, simulations show that even the tiniest adjustments in conditions can significantly impact Pluto's trajectory. Though Pluto's orbit is stabilized by mechanisms like libration and precession, simulations have also revealed that it is far from consistent. Small deviations in initial conditions can lead to vastly different outcomes, making long-term predictions extremely challenging. Despite this apparent chaos, Pluto's orbit remains relatively stable over geological timescales, suggesting that even in the midst of seeming randomness, there is an underlying order to Pluto's motion around the Sun. Predicting celestial movements, especially for objects with irregular orbits like Pluto's, is a massive challenge, and any long-term forecast contains uncertainty. Numerical models help us comprehend and anticipate these movements, but their accuracy is heavily dependent on precise initial conditions. Even a slight error can result in vastly different outcomes, making it hard to predict Pluto's future trajectory with confidence. Unanswered questions that demand deeper exploration. Tyson emphasizes that while the probability of an actual collision between Pluto and Neptune is astronomically low due to the resonance and orbital mechanics discussed earlier, the mere theoretical possibility invites valuable discourse on celestial dynamics and chaos theory in astrophysics. Similarly, Michio Kaku, a renowned theoretical physicist, shares this curiosity. While he acknowledges that the stable 3:2 orbital resonance between Pluto and Neptune prevents a direct collision, Kaku points out that space is not a closed system. Gravitational perturbations from other bodies or even the hypothetical presence of unknown distant objects, such as Planet 9, could over time alter these orbits in unexpected ways. These possibilities, while speculative, illustrate just how interconnected and fragile the cosmic ballet really is. Both experts agree on one central theme: Pluto's behavior in the solar system is a gateway to broader scientific inquiry. Its eccentric orbit, tilted inclination, and periodic closeness to Neptune serve as a real-time case study for understanding nonlinear systems in space. When simulations are run with minute alterations to Pluto's starting trajectory, the results can show massive deviations in future paths, some that bring Pluto closer to other celestial bodies, and others that eject it from its current orbital range altogether. This sensitivity to initial conditions is a classic hallmark of chaotic systems. However, despite the provocative headlines and dramatic possibilities, the scientific consensus remains steady. Pluto is not on a collision course with Neptune, at least not within any time frame relevant to human history. The stabilizing factors, including the orbital resonance, inclination, libration, and the gravitational interplay with Jupiter and Saturn, act as an invisible shield, preserving the fragile harmony of the outer solar system. So, are we witnessing something unusual? Yes, but not in the form of impending doom. What we're witnessing is the universe revealing its complexity, its elegance, and its unpredictability. The attention brought by figures like Tyson and Kaku highlights the importance of continuing to observe, model, and question what we think we know. In this dance of planets and dwarf planets, the real collision might not be physical, but intellectual, where our current knowledge meets the unknown, and science pushes forward. In the end, Pluto's tale is less about danger and more about discovery, a distant, icy world still teaching us about the rules of the cosmic game. Unanswered questions: Pluto and Neptune. Will Pluto collide with Neptune, or is this merely a momentary confusion in the universe's ever-changing state system? Only time and further research will provide the answers. For now, we are left with an even greater curiosity: how much is still unknown about our own solar system? The possibility of a Pluto-Neptune collision invites further examination of the universe's mysteries and challenges our knowledge of planetary dynamics. The idea of two heavenly bodies with drastically different properties colliding raises fascinating questions regarding gravitational interactions and how they shape the evolution of planetary systems. A collision between Pluto and the Sun, or Neptune, would not only have significant repercussions for our understanding of planetary behavior but also provide valuable information about the evolution of the solar system itself. To understand the dynamics of a potential impact between Neptune and Pluto, it is essential to consider the characteristics of the two planets. Though Pluto is classified as a dwarf planet, it includes a variety of components and compounds in a frozen state, thanks to the icy outer solar system's extreme cold. Its surface is covered with nitrogen ice, and the atmosphere is primarily composed of methane, nitrogen, and traces of carbon monoxide. In contrast, Neptune is a massive gas giant primarily consisting of helium, hydrogen, and other lighter elements, with a deep, dense atmosphere. A collision between these two vastly different bodies would undoubtedly have a significant impact, conceivably triggering an event observable at great cosmic distances. However, it is essential to keep in mind that Neptune's gravity is not the only stabilizing force at play. Jupiter, the largest planet in the solar system, also possesses a substantial gravitational pull, contributing to Pluto's stable orbit and keeping it away from too close proximity to Neptune or Saturn's domain. The influence of multiple gravitational sources complicates interactions in the outer solar system, making a catastrophic collision between Pluto and Neptune highly unlikely. While Neptune's gravitational influence plays a dominant role in stabilizing Pluto's orbit, the complex relationships between other planets like Saturn and Jupiter further ensure that Pluto's path remains steady. Research has also shown that the connection between Pluto and Neptune is not as straightforward as a potential collision course. The gravitational resonance between the two planets, where Pluto completes 2 orbits for every 3 Neptune completes, creates a natural barrier that prevents them from colliding. Frequently described as a gravitational dance, this resonance ensures that their orbits, while intersecting, never result in a collision. This mechanism is an extraordinary example of how celestial bodies can maintain a harmonious relationship despite the chaotic forces at work in space. Yet, the future of this delicate balance is not guaranteed. Small shifts in the positions or velocities of these planets could disrupt this resonance and lead to unpredictable consequences. These shifts could be triggered by external forces, such as the gravitational influence of a passing planet or an undiscovered star, or by internal events like tidal forces gradually altering their orbits. Continued study, along with ongoing observation of Pluto, Neptune, and surrounding bodies in the outer solar system, is essential for understanding their long-term stability. As new technologies emerge, scientists will be able to refine their models and gain a clearer understanding of the dynamics between these distant objects. New data may shed light on the delicate equilibrium that keeps Pluto and Neptune from colliding, or it may uncover entirely new forces that could alter their relationship in the future. As we continue to study the dynamics of Pluto and Neptune, one key factor that has emerged is the possibility of an undiscovered object influencing their orbits. This hypothetical object, often referred to as Planet 9, is believed to exist in the solar system's farthest reaches. Some scientists have speculated that its gravitational pull could alter the orbits of objects like Pluto, potentially pushing them toward new routes that could affect their current stability. While the existence of Planet 9 is still a subject of debate, its potential impact adds another layer of complexity to the situation. In addition to gravitational interactions between known planets, it is important to consider the broader context of how the solar system functions as a whole. The Sun, the dominant gravitational force in the system, is gradually losing mass through the process of solar wind. As the Sun's mass decreases, the orbits of all planets, including Pluto and Neptune, could slowly expand over time. This process could change their relative positions and influence their long-term orbital stability. Furthermore, the outer solar system is not a static place. Comets and other small objects are always moving through it, exerting their own gravitational influences. These passing objects could occasionally disrupt the orbits of distant planets like Pluto, though such occurrences are rare and improbable. The combined effects of these varying forces may ensure that Pluto's orbit remains dynamic, constantly adjusting in response to the gravitational dance between the planets. On a more speculative note, the possibility of a massive event, such as the collision of 2 smaller bodies in the distant reaches of the solar system, may also play a role in changing the paths taken by objects like Pluto. If such an event were to occur, it could set off a chain reaction that might impact Pluto's path in ways we cannot currently predict. This highlights the chaotic nature of celestial dynamics, where barely noticeable changes can result in large-scale consequences over time. Understanding these potential scenarios requires sophisticated simulations and constant observation. Though we currently have a good grasp of Pluto's orbital behavior, the true nature of its future course will be determined by a plethora of difficult-to-foresee factors. The ongoing study of Pluto, Neptune, and the outer solar system remains an essential component of modern astrophysics, offering insights into the forces that govern our cosmic neighborhood. As our observational tools grow more precise and our computational models more advanced, we edge closer to unlocking the secrets of planetary motion on the fringes of our solar system. Missions like the New Horizons probe have already provided invaluable data about Pluto's geography, composition, and atmosphere, but there remains so much more to uncover, not only about Pluto but about the countless other icy bodies that populate the Kuiper belt. This distant region, beyond Neptune's orbit, is filled with trans-Neptunian objects that may hold the keys to understanding the solar system's early formation. The gravitational tug-of-war between these bodies, along with interactions involving Neptune and even hypothetical Planet 9, paints a picture of a far more dynamic and volatile outer system than previously imagined. The delicate interplay of these forces reminds us how fragile yet resilient orbital relationships can be. A single rogue object, a stray asteroid or undiscovered dwarf planet, could, over millennia, shift the gravitational equilibrium and send ripples across planetary paths. This is not just a theoretical concern but a reflection of the chaotic, ever-evolving nature of space. Moreover, the study of Pluto and Neptune transcends our solar system. It provides a template for understanding exoplanetary systems, where similarly complex interactions might govern the behavior of distant planets orbiting alien stars. The principles of orbital resonance, gravitational capture, and dynamic stability are universal, applying as much to the TRAPPIST-1 system as to our own backyard. In this light, the Pluto-Neptune relationship is more than a question of potential collision. It is a cosmic lesson in balance and persistence, a celestial choreography that has endured for billions of years. And yet, this equilibrium, like all things in the universe, is not permanent. It evolves. Ultimately, the fate of Pluto, Neptune, and the outer solar system will be shaped by a blend of known physics and yet undiscovered phenomena. Whether or not they ever collide may be less important than what their interaction teaches us, about gravity, about time, and about our place in the vast, unfolding story of the cosmos.